Good day, everyone. We are going to record the lecture on multiple linear regression model. So an extension of the bivariate simple regression that we've discussed so far. I hope that you've been able to keep up with the assignments and homework and raised all the questions that need to be resolved before we can understand and build on what we did before. So let me share some slides with you to facilitate our discussion. So going from bivariate to multiple means we still are explaining one dependent variable, but with many x's, multiple x's. We don't have a multivariate regression because that would mean explaining together a lot of outcomes. Still linear, still additive, but with k regressors and one intercept. So k plus 1 unknown coefficients in this model. Example would be in the wage equation, you're adding to education experience, tenure, number of years since college or since birth. And this would have been normally included in this error term, but now we are bringing it out, making it more likely that education will not be correlated with the errors. The average score is another example, expenditure by family on their student and average income of the family. These two are likely to be highly correlated, expenditures with the family income. And so still, we're trying to bring in some effects of income or household characteristics in terms of explaining average outcomes, educational outcomes. Another example of how multiple regression allows us to bring in factors, considerations that were not possible with the bivariate regression is this example. Consumption, family consumption, let's say, is a function of the family income, but it's not linear. So we put in income squared. This makes it a quadratic function, a nonlinear function of income, but it's still linear in betas, right? So multiple regression that we will discuss will still be a linear regression, not because the variables are linear. And so this shows you how x1 could be income, x2 is income squared, right? Why not? And then you might have x3, x for other variables. The interesting thing is this also resolves another problem. If you were to look at this relationship between income and consumption, look at the scatter plot of your data, you'll find that it's not linear. You can certainly put a line on top of your scatter plot, but too many points are too far away from it. What you might find is it kind of peaks that curve at some point, and then it declines. You can draw this in here. So this is consumption, this is income, and you might find that it does something like that. So at some point, more income isn't going to increase your consumption, but it does non-linearly reach a peak. That's what this function will get you. So what is the impact of income on consumption in a model like this? It's not just going to be beta, right? You have to take derivatives. The change in this plus the change in income, that's beta 1, plus the change in this is twice beta 2 times income to power 1. That's a derivative of this function. And so the change in consumption relative to a unit change in income depends on what income you're talking about. It moves with income. It's not free of that independent like we had in a bivariate regression. That's good. This may not be the best functional form for this situation. Depends on your data, right? This is just an example. But the point is, ceteris paribus impact now becomes a function of the variable itself. It moves with it. So you can do that with multiple regression. CEO salaries is a function of sales and tenure of the CEO. Experience might be an indication of how efficient a manager the CEO might be. And you could look in terms of logs. Logs is sort of a elasticity for beta 1 in terms of sales. But in terms of the impact of experience, tenure is nonlinear. Up to a point, it increases in value, but then it just turns down, assuming beta 3 is positive. So the multiple regression is allowing you to include additional variables. You could put these in any scale you like, logs, cosines, the squares, and whatever, and other variables and their powers, beginning to look at the polynomial regression, every variable being included and its higher powers. Maybe we'll let the data speak, right? This is what, in a way, big data methods, data science these days is doing. Try all kinds of functionals and as many variables or factors you think are important, and let the data speak. All right. Now let's say we have the data, sample size of n, and we've used it with least squares method, minimizing some of residual squares, just like before. And we have obtained estimates for betas. Yi minus its fitted value with k variables is the residual, right? We want to find those values for betas, k plus one of them, such that this is minimized. These would be the solutions. We'll talk about what kind. But each of these betas, take beta j, is the ceteris paribus impact of xj given a unit change in xj on y, if all the others are kept fixed or not changing, comparable. So when I look at the changes in that equation, I'm assuming dy by dxl, all the other x's, is equal to 0. There is no change. Okay, that's the sense in which multiple regression is helpful in terms of determining partial effects of variables, given there are other variables. Why do I need other variables? As you'll see even more clearly in a moment, it's because I couldn't run a perfectly randomized experiment in which my variation in target variable xj and y had nothing to do with what values these other variables take. I can't do that, so you'll see that my trick to compensate for that lack of perfect experiment is to include factors, other variables, higher powers of variables that I think might control mathematically, statistically, for what my bad experiment did. I'll jump over this. Come back to this GPA, a college GPA as a function of high school GPA and the scores, ACTs, achievement tested scores. And each of these have the usual interpretations. We've had another 10 points in ACT. This is 10 multiplied by this. It's associated with 1 point. 10 times this is almost 1 point change in college GPA, given all else being equal. What properties would OLS have? We have a lot of derivations that we skip in this course. I will come back to them parenthetically and discuss them, but they will not be required. Matrix algebra, vector algebra would really help to take care of those general case derivations. But in this course, I'm not assuming we know we can use vector algebra. So this is the fitted value, right? Hats, least squares residuals, right? And if I do a good job of minimizing some of the squares of these are the equations I have to solve, will solve to get my betas. Remember, this is exactly what we had for bivariate regression. Given that there is an intercept in this model, sum of residuals still have to add up to 0. That's tantamount to saying y bar and x bars have to be on the regression line. Y bar and all the sample means will always be on the regression line that you fit if there is a beta 0. This other one is familiar too, right? Forget about the j. Xi ui hat equal to 0 is what we had for bivariate regression. Now we have more than one x. We have k of them. For each one of them, this has to be true. So x's and u's are uncorrelated in the sample. Okay. How many equations? 1 and 1 for each x. There are k of them, so k plus 1 equations for k plus 1 betas, including the intercept. As many equations as there are unknown coefficients. There is an interpretation, call it Frisch-Wu, partialing out auxiliary regression, interpretation of multiple regression, and it tells us why things work. What do I mean by things work? Remember the bad experiment? I'm only interested in the impact of education on wages, and because I didn't randomize assignment of education levels, I have experience, ability, family income, and all sorts of other factors that have to be controlled for. So how does a multiple regression do that? Compensate for a bad experiment. Imagine regressing the explanatory variable education x1 on all others. Electronics, modern technology these days, right? So I'm only interested in the impact of x1 on y, but I have other variables. Let's regress x1, or explanatory variable of interest to you, on all the other explanatory variables. Get the residuals. This will give me, without loss of generality, R1 at residual from regressing 1 on all the other variables. Okay? And for each observation, I'm going to get one residual, right? So regress x1 on all the other variables, get the residual. Now regress y, the original dependent variable, on this residual. That's a bivariate regression, right? Simple regression. Believe it or not, if I run this regression, yi, let's give the name of a constant beta 0, beta 1 or I1 hat plus some error. If I ran this regression, I would get an estimate for these residuals. I deliberately put beta 1 because that estimate will be the estimate of beta 1. Why is that so? Interpretively, I can prove this algebraically, is that the residual of a regression like R or R1 is uncorrelated with all the regressors in it, all the other regressors. Remember? This is for any regression. If I run a regression, the residuals of that regression and its explanatory variables are uncorrelated. So by regressing Y on R1, I am regressing Y on something that is no longer correlated with x2, x3, x4, all the other x's. By construction, these are least squares residuals of x1 regressed on x2, x3, and so on. So it's uncorrelated with those other x's. And so I am regressing y in the second step on a purified, expunged, controlled for x1 from the influence of x2's. What influence? Whatever influence I think they should have in the regression. I projected them out. This works. This Frisch-Wu partialing out is brilliant, and it tells you why multiple regression works to account for, to compensate for bad experiments, why it's become the workhorse of observational studies that includes all of social sciences, where we can't conduct perfectly randomized experiments, controlled experiments. Generally speaking, other fields use multiple regression as well because there is no such thing as a perfect experiment. By the way, I'm going to give you a formula for beta 1 hat in multiple regression. We said we are regressing y to the center rate on R I1. Why do I not have minus its mean? Because residuals in every regression or less regression sum up to 0. The mean of residuals is 0. And then sum of the x's squared. The x's here are residuals, right? So this is the familiar bivariate regression slope coefficient, except that the dependent variable is still y, but the independent variable is cleaned up, x1, cleaned of the influence of all the other x's. The formula is the same. Some value interpretively, but the computer doesn't actually compute this. The computer works with the k variable case and optimizes overall. It's object programming. Each object is a matrix. Each matrix can be a vector, each vector can be in a scale, like what we are doing here. I'll come back to this a little bit more. Goodness of fit, the same definition, the same interpretation. If you have an intercept, total sum of the squares of the y's is equal to explained bit of it and the residual bit of it, and r squared is the ratio of the explained to the total. And if you have an intercept, you can use this formula. Remember I mentioned to you a better formula and a better interpretation for r squared is the correlation coefficient squared between y and y hat, the observed and the fitted values. It's a measure of linear goodness of fit. And so covariance between these two, yi hat is squared. If you have an intercept, this y hat bar arithmetic mean is just y bar, and divided by variances of yi's and yi hats, a preferred formula. So a couple of examples explaining the number of times someone is arrested in 86. Depends on proportion of prior arrests that led to conviction, months in prison, and quarters employed. You would think the more employment a person gets, the less likely negative they are to be arrested to commit crime. And if they've spent a lot of time in prison, they may not like that and commit less crime. And prior arrests seem to be a deterrent. People seem to learn. Not a very big R squared. And again, we'll learn to discover whether that's significant or not. If I add average sentence in prior convictions, not just time served, but the severity, it seems like it's contributing to the number of arrests. So it's not reducing the number of arrests. However, this is very close to zero, right? It may be different from zero. We'll learn how to test for the significance of this. How different from zero is it? R squared is still very low. It's not a lot of explanatory power to this regression. Maybe there are other variables that matter. Maybe the functional form is wrong. Maybe number of crimes have nothing to do with these individual effects. The question of macroeconomic situation, prior life experience, and so on. R squared seems to go up a little bit, at least not go down, when I add variables to a regression. There's a good reason for that. R squared is a non-decreasing function of the number of explanatory variables. The more variables I add, the larger this becomes. It's just another term, another term, and another term that is non-negative. So adding variables to a regression should not, will not decrease R squared. It may not change it by very much, but it cannot decrease it. So it's a sort of perverse thing. Regression running, perverse behavior by some scientists is to try to get a good R squared by adding more and more variables. In big data, of course, they don't use a linear regression, and there's penalization methods, which I'll talk about briefly as we go through this course. But fit, as measured by things like R squared, are always going to look really good because you're trying in everything that is relevant to individuals or firms or stock market returns. And R squared can suffer from that. All right. So what properties do these estimators have? Remember, we had a parallel discussion for bivariate regression. Are these estimators biased? What's their variance? To determine how good, precise our statements are about these unknown betas, partial effects. So we assume linearity in parameters, not variables. Random sampling, as I mentioned, is strong, and we'll relax this. Means every unit observed is picked randomly and then put back in another random draw. Independent draws from the same population, the same mean, the same variance, the same distribution. And remember, assumption 3 was a little bit different for bivariate regression. We only needed xi's to be sufficiently variable right? Remember this, xi minus x bar squared. We needed this to be large. The larger it was, the better, because the variance of OLS's slope was inversely related to this. Here we have many x's, so what we struggle with, what we're challenged with, is that a lot of these factors, covariance x's, are related to each other. In fact, if they were not related, we wouldn't bother. They matter for a regression, as you will see, only if they are related. But if they are too closely correlated, they cause ambiguity in terms of discovering what the partial effect of each variable is. They don't impact existence of OLS solutions or their statistical properties, as in unbiasedness. Multicollinearity does not cause bias. It's an identification problem. It's a precision problem in terms of what the statements you make, how precise, how large a variance you attach to each beta hat. So we'll see. I'll clarify this much more algebraically in a bit. I just don't want x's to be too correlated or exactly correlated, exactly related. And think of this previous example we had, average of score, expenditure by family and family income. Suppose this was always like 40% of this. That's an exact linear relationship between x1 and x2. We don't like that. There's nothing that I can learn from average income of the family that I couldn't have learned from expenditure on each student. It's the variability. There is no new variability information. Think of putting here, for this other example we've encountered before, percentage of vote for candidate A as a function of share of campaign funds on A and candidate B. The total is 1, right? 30%, 70%, 50%, 50%. And so these two always add up to 1. That's equal to the 1 for the constant. That won't do. That's exact multicollinearity. These two add up to this third hidden variable, constant. So one of them have to be dropped. The constant has to be dropped. We can't proceed in this exact case. There will be a failure. You don't have to worry about it. The computer will come back crashed as it couldn't converge. It couldn't get you an estimate. So exact multicollinearity, you will always know about. It's very, very close relationships. There are approximate multicollinearity that cause problems because nothing fails. Estimates come back. They're unbiased, but massive variances, as you will see. Fourth assumption is the same as before. Expected value of u given x is 0. Here I have kx's. Conditional mean equal to 0. 0 conditional mean assumption. And this is more likely to hold now in a multiple regression compared to a bivariate regression. Why? If I only put x1 in this regression, some of these x's will be shoved into the error term u, the idea that x1 and u are independent, or the mean of ui, which now may contain x2 and x4, being 0 for any value of x1 is not true if these are correlated, right? So, as in big data, the more variables you throw in, the higher the R squared, and the less likely that this assumption will fail. Right, remember, again, functional form, as we saw, like the square of income, can be a problem if this relationship is really nonlinear. Those nonlinear terms will be in U, and this assumption will fail to hold. Um, a little bit of discussion, very important in terms of doing empirical work and making decisions about model building, empirical strategies, depends on understanding the consequences of mistakes. So you start with the most classical examples of misspecification. Um, Suppose you have an irrelevant variable that you have mistakenly included in your regression. Big data people do that all the time. They throw in everything. What aisles you visited, you know, characteristics of your wife and your husband, your kids, what cities you go to, what pages you browse, and your education, your age, and everything goes in there. And some of them may not be relevant. Um, Invariably, many of them are not. In fact, our priors in a lasso method, in a big data method, is that many of them are, in fact, without a partial effect, without relevance. What's the consequence of doing that? It's a simple setting. I put this x3 in the regression, but it's okay. It's when it's 0. So when I run this regression, my estimator under the assumptions 1 to 4, in fact 1 and 4 is sufficient, um, will give me an unbiased estimate. So I'm not going to get a bias cost to including irrelevant variables. In contrast, if I exclude a variable, it seems like we pay a severe price. It's both statistical and interpretive that is severe. Think about it. Suppose this is the true model with 2 regressors, 2 slopes. I go ahead and estimate the model without x2. So I have an omitted variable problem. When I estimate this bivariate, notice we put tildes, not hats, so that we distinguish these estimates from the estimates of the true model, beta 1 hats. I don't like the use of beta 0 and beta 1 here. Don't know if I've chatted with Jeffrey about this, but I prefer different coefficients because there are different coefficients. But suppose you do this, then you want to see what cost you pay by omitted variable. So this is a problem if x1 and x2 are correlated. The omitted variable x2 is correlated with the included variable x1. They're not, you'll see there is not a problem. Correlation doesn't mean x2 is related to x1 in this fashion. That's just one way it could be, right? So suppose the omitted variable is related to the included variable in this fashion. That makes sure they're correlated. So I replace in the true model with x1, x2, replace x2 with this function. Collect terms, the constants, the ones that involve x1 and the error term, right? So what do you think? If I ran a regression of y on x1, the bivariate regression, if there is no x2, I'll get beta 1. If there is x2, I'm going to get an estimate of this whole lot. I may or may not know it because I'm only running this bivariate regression. So we're doing a counterfactual. Were there to be an x2 that is omitted, the bivariate estimator of beta 1 hat, they were called beta 1 tilde, that you get from this regression is really an unbiased estimate of all of this. Beta 1 plus beta 2 delta 1. What's beta 2? Is partial effect of x2, were it to not to be 0. What's delta 1? Is a degree of correlation, dependence between x1 and x2. Again, I will elaborate on that later on without having this kind of relationship. So my estimate, beta 1 tilde, from the bivariate regression, beta 1 tilde, is going to be having an expectation equal to this guy, which means it's not beta 1. So this is beta 2 times delta 1 is the bias, is what's stopping my OLS estimator to be unbiased for beta 1. Okay. Omitted variable bias depends on partial effect of the omitted variables and the degree of relationship between omitted and included. This would be the case for the Mincer equation we've encountered before. If I account for ability, or I should, and I'm not, then ability is shoved into the error term. And if I just regress this bivariate, delta 1 hat estimate in this regression will be really an estimate of all of this. Impact of education partial, impact of ability, and the relationship between education and ability. So I have a bias in the simplest of the Mincer equations. If I just look at wages and education correlation between, a lot of newspapers do that. So these people with this level of education, this number of schooling get this much wages, and so on and so on. They're not controlling for experience, ability, location, skill sets, and all sorts of trades. We need to do all of that before we can make sense of these numbers that they throw at us. When is there no omitted variable bias? When there is no relationship between omitted and included. We don't have to worry about that experimental failure we talked about. If some characteristics of individuals does not matter, I don't have to randomize with respect to it. It's automatically irrelevant. Therefore, I don't have to include in the regression either. So when there is a correlation, I need to. You see the dilemma, or you will see the dilemma. I worry about including these variables when they're correlated. That's when I should take care of them. I need to run this regression rather than this, so that I get estimates for beta 1, beta 2 separately. At the same time, if they're too correlated, I get multicollinearity. I will still get beta 1 and beta 2 separately in this bigger regression, but as you will see, I'll get very large variances. Okay. When you have multiple variables included and then some variables excluded, it's much more difficult. The bias is there. It's much more difficult to sign it, to talk about the nature of that bias. Okay. And in your data sets and your exercises, you progressively include more and more variables and keep revisiting the estimates you get. I could add a dummy variable for gender to account for that as well. See if that's important. You'll learn to do that. So, adding the assumption of homoscedasticity is necessary if I want to obtain a variance formula for you, or find which variance formula is appropriate for least squares. Again, we saw this in chapter 2. Variance of u given x's has nothing to do with the x's, because u's and x's are uncorrelated in this model. And this heteroscedasticity means that sigma squared I doesn't have anything to do with the ith person's characteristics. You can see in this example how unlikely that is to be true. A variation of wages around the mean, this is error around the mean, right? Wages around the mean are very unlikely not to depend on these variables. We see it in the data, they do. So you have heteroscedasticity. That's being, if you assume that away, right? You can write it in this simple way because xi is written as a vector of k dimensions. All the k's here is symbolic. So given the 5 assumptions, given assumptions 1 and 4, I can prove unbiasedness. Given assumptions 1 to 5, or weaker versions of it, I can derive the variance of each coefficient, this beautiful form. Again, this is not what the computer is going to compute for multiple regression, but we get a lot of mileage out of it to interpret things. Sigma squared, can't do much about that. It's always there. Variance of the statistical statements I make depend on variability in the data, the yi's, or the errors. SSTJ is the variability in the jth regressor in the sample. That's good because it's reducing this variance. The larger that is, the better. And then there is this inflation factor, 1 minus Rj squared. What's Rj squared? Remember, this is the jth variable coefficient, jth variable variability, and now Rj is the coefficient of correlation, or the R squared of a regression of this xj regressor on all the others. Remember, we used to do that to get the residual in the partialing out interpretation. That's the R squared of that regression. So imagine xj not very correlated with all the other x's. This would be close to 0. This becomes smaller and smaller. 1 minus 0 is 1, right? So that's large, close to 1. And that becomes close to the formula it would have in a bivariate regression. Otherwise, for any other degree of correlation, this is less than 1. So this would be larger than a bivariate regression. The larger the number of regressors, the bigger is the variance of each of the partial coefficients, partial effects. More variables, we learned, are relatively less costly because you don't incur a bias cost of omitted variables. You want to protect yourself against omitted variables by including, but now you realize that you're paying a price in terms of higher variances. Suppose that some xj regressor is highly correlated with all the other x's. This gets close to 1. 1 minus 1 is almost 0. Divided by 0 is infinity. So adding more and more variables causes increasing degrees of uncertainty about what you say about their separate partial effects. This does not affect R squared of the regression. Remember, R squared can't decline as you add variables. So you're loving it by adding variables, being a data scientist with big data, getting better and better R squared. You actually get better predictions. But in terms of saying what causes what, hell breaks loose. The variances of each of these partial effects causes becomes larger and larger. So I could tell you next quarter's unemployment would be 4%, give or take infinity. Something to think about. So the error variances contribute, of course, how much variation there is to be explained. And variation in x's is good, covariation in x's is bad. Omitting variables is bad, you pay a bias, but you get the smaller variances. All of those have to be considered in practice. For an empirical person, all of these decisions have to be made and made statistically. We've talked about these things so far, like these are mathematical objects to consider. Decision making has to be statistical, subject to probabilities, reported statistically, subject to uh, uncertainty. You have to make probability statements. So we need to do it inferentially. In statistical inference requires the distribution of these beta hats and distribution of R squared. That's chapter 4. Okay, we've talked about this. Now you can see why multicollinearity matters, because if you have multicollinearity, then the R squared J that I talked about would be equal to 1, and you get infinite variances. Computers don't compute infinity. If they divide by 0, they collapse. They report the problem. But it's as you get close to perfect multicollinearity, you get close to infinite variances. We learned that infinite variances often mean you obtain insignificant coefficients, so you have some clue about which coefficients, which regresses to draw. Examples of multicollinearity, the average score from the course that you observe, a particular level, teacher experience, expenditure for instructional material, expenditure for other purposes in school. These are likely to be highly correlated. That's okay. That's why you have to put both of them if you want to know the partial effect of each, right? But you get less certainty about beta 2 and beta 3. You could combine them, total expenditure. You get a more precise estimate of the impact of expenditure, but you can't tell what the details are. You could drop some independent variables. Insignificant. How you do that has a statistical implications, and we'll learn some means of analyzing that and to try to make good decisions with that. This inflation factor, remember, this multiplied by the variance of beta hat j from a bivariate regression was the variance of beta hat j in multiple regression. This could be something you look at, and if you find that this is very large, that's grounds for suspecting multicollinearity and also a suggestion of which xj to drop. This is very large. Excuse me, if this is larger than 10, Wooldridge will tell you, some empiricists will tell you then you need to drop xj and successively. So that's difficult. This 10 itself requires artistic license. So variance is a misspecified model. So this is the true model. This would be the estimates of the betas in the true model. We just looked at the formula for these coefficients and their variances. Were you to estimate the wrong model, the small model, you get the tilde estimates, and you get the formula for the variances of bivariate regression, which would be this, remember, y on x1. Now you've run a regression of y on x1, x2, so you have to adjust this formula by the inflation factor, 1 minus r1 squared, correlation coefficient, r squared of regressing x1 on x2. And variance in the smaller model is always a smaller variance in the larger model. If beta 0 is truly 0, you've committed no error and estimated will be unbiased. If beta 2 is non-zero, that means x2 does belong to the model and you excluded it. um, you're not going to get an unbiased estimate. Okay, you get an unbiased estimate beta hat in the true bivariate regression, excuse me, trivariate regression, but you will not get an unbiased estimate in the bivariate regression. This is beta tilt. And variance in the small model still smaller than variance in the large model. So bad models look very certain, less ambiguity about things. If you know less, you sound stronger. You have stronger opinions. You can make a stronger statement. Well, in order to report the standard errors for these things, we need to have an estimate of sigma squared. We covered this before for bivariate regression. Sum of residual squares is a good candidate for this variability. You just have to average it right. Divide by n. But if you want an unbiased estimator, then you need to adjust this to degrees of freedom. Sample size minus the number of coefficients you have to estimate to fit the model, which is k plus 1 coefficients. And then you put those estimates in this formula, like so, and you're going to get the standard errors if you get the square root of that. And those are the things that are reported by computer outputs. Lastly, today, what's good about OLS? It makes sense to minimize some of residual squares. With what kind of properties can I come up with another estimator that in some respects is better than OLS? The general answer is yes, but under certain circumstances, very important ones, you can't beat OLS. What does that mean? Gauss-Markov theorem. If you look at the class of linear estimators, this is beta j tilde, could include beta hat. It's the weighted sum of yi's. These weights define different estimators, OLS, GLS, instrumental variables, maximum likelihood, all kinds of things, GMM. I'll show you what these are for OLS. That's the extra lecture I promised you to show you how these formulae are arrived at to give you a better insight. So among the class of linear estimators that are unbiased, meaning expected value of all of them is equal to beta j, with the classical linear regression assumptions 1 to 5, all of them. Among this class, the one that cannot be beat in terms of variance is OLS. Other estimators may have a variance that is equal to OLS, but none of them can have a variance that is small. Gauss-Markov theorem proves that. Only in the linear regression model with the 5 assumptions, homoscedastic, random sampling, or slightly weaker than that, you will get this result. If you are willing to take nonlinear estimators, or if you are willing to give up on unbiasedness, so consider biased estimators. In real life, most estimators are biased anyway, so you might as well give up on it. Then you get better estimators. Big data lives on that. Shrinkage estimators, and Stein estimators, and ridge estimators, all sorts of others are willing to pay a cost in terms of bias or relax linearity and so on, and get estimators that have a smaller variances. So Gauss-Markov theorem is very boutique, specialized set of results. And it is stated here. All of unbiased, then variance of OLS cannot be larger than variance of any other linear unbiased estimator. Blue, best linear unbiased estimator means best means minimum variance. Okay. I'm going to look at the situation where I have multiple regression with a whole bunch of controlling variables, and I'm interested in some kind of treatment. Remember the causality issue that we discussed. So this one is a discrete treatment variable, 1 or 0. Get treated or not treated. You vote or not vote. Buy or not buy. Get trained or not get trained. And controlling for these other variables makes the assumption we made earlier is randomized assignment to groups in such a way to make the outcome not dependent on participation given these variables, makes for causal inference about the impact of W. Notice these would be tau i's, treatment effect for individual I. If I assume they're all to be the same or take the average of them, this is the coefficient I'm going to get for this 1, 0 regressor. So I have all kinds of regressors plus this 1, 0 variable and coefficient, Euler's coefficient of that. If I've done a good job of controlling for all the x's, would be an unbiased estimate of the average treatment effect. Average treatment effect of participation in this training program. All right. I want to wish you a good day. Please look at Canvas, all the assignments, the practice ones, both computer-based and from the problem sets from Jeffrey Wooldridge's book are in MindTap. That's something you've all registered for. You could practice those. The assignments that have grades are announced on Canvas with the deadline for delivery. The solutions will be posted upon the deadline, so we can't really grade them after that. You have a great one, and I'm going to start with inference, a little continuation of this multiple regression. But okay, what kind of probability statements, what kind of distribution do we have for these estimated objects? Best to you, and I'm going to stop the meeting.